Time for 12.5 collision theory. Here we're going to use the postulates of collision theory to explain the effects of physical state, temperature, and concentration on reaction rates, define the concepts of activation energy and transition state, and use the Arrhenius equation in calculations relating rate constants to temperature. So collision theory basically states that reactants, either atoms, molecules, ions, whatever, have to collide in order to react with each other. And there's three different postulates. The rate of reaction is proportional to the rate of the reactant collisions. Okay, so the more collisions per time, the higher your reaction rate. Makes sense, right? You're going to have a faster rate if the collisions are happening more often. But not every collision can lead to a reaction, bringing us to the second postulate. Molecules have to be oriented properly when they collide. So they have to collide so that they can form an intermediate, for instance, or so that we can break bonds and form new bonds. If they collide and it's not in the right orientation, then that bond breakage may not happen. And our third postulate also, the molecules have to have enough kinetic energy to react. They have to be moving fast enough. If the kinetic energy that is given to it is not high enough, you're not going to be able to break chemical bonds and form new ones. So, for instance, let's say I have a basketball and a baseball, and I want to make them collide and stick together. If I throw the baseball and my friend throws the basketball and they hit each other at the right spot, they're probably just going to bounce off each other, right? They're not going to stick together. And that's because they don't have enough energy. And it would take a crap ton of energy to get them to actually stick together, right? It's not going to happen but it's just something to think about to be able to visualize this. So yeah, if the energy is too small, they're just going to bounce off each other and not react. This energy, the energy that is needed to break and form new bonds is called the activation energy of a reaction. So this is the minimum energy necessary to form a product during a collision between reactants. So for instance, if we're looking at the reaction of carbon monoxide and oxygen, so the reaction is 2CO plus O2 gas forms 2CO2 gas. If the oxygen side of carbon monoxide collides with the oxygen molecule, nothing's happening because the carbon is what's bonding to the oxygen. So if these collide, there's nothing happening, no reaction. Whereas if the carbon side of CO collides with O2 with enough energy, then you can form that CO bond and then break this oxygen-oxygen bond. So that's forming more CO2, as long as, again, there's enough energy. So we're going to look at reaction energy diagrams. And the way these work is your y-axis is your potential energy. And your reaction path or extent of reaction is on the x-axis, aka there's really nothing on the x-axis. Sometimes it's time, but yeah. So you have some reactants and you have this energy barrier that they have to get over. And then if they form an intermediate, they form what is called an activated complex, and that happens at the transition state. So reactants form an intermediate called the activated complex. Let me make this a little bit more obvious here. Hold on. There we go. So at the tippy top is where you have your transition state and where your activated complex forms. So your activation energy, oops, I did this wrong. Let's try this again. There we go. Your activation energy is your energy from the bottom of where you started to the energy at the top of your reaction hill. And then your enthalpy, delta H, is here. And there's your delta H. So up till now, we've talked about concentration and rate, and then we just did concentration and time, and now we're going to look at temperature and rate. So in general, our rate of reaction increases with temperature. So if you want to cook something quicker, you raise the temperature of the oven, albeit you can burn things, or if you want to cook an egg quicker, you raise the temperature of the frying pan, right? Turn up the heat on the burner. Now, it's not the best idea to make something like scrambled eggs if you want them nice and creamy and delicious, but if you got to make them quick, you got to make them quick. If you want to slow the reactions that lead to food spoilage, you put your food in the refrigerator, so then it doesn't spoil as fast. And if you really want to slow it down, you put it in the freezer. But food still spoils, just takes a much longer time. So here's the plot I was trying to make a lot prettier. Some A plus B reactants. Okay, they require this EA energy to be put into this reaction for it to hit this transition state. And once it hits that, then the reaction proceeds downhill to where we make our products. So now let's say we want to look at the reverse reaction of this, which is what I was first drawing. The reverse reaction activation energy is higher, and its total is equal, that difference is equal to delta H. So the EA in the reverse reaction is equal to EA of the forward plus delta H here. Kind of cool. So let's talk about kinetic theory some more. Temperature is a measure of the average kinetic energy of molecules. The higher the temperature something is, the faster the molecules are moving. So again, higher temperature, higher kinetic energy. The higher the temperature, the larger fraction of molecules that have kinetic energies that are equal to or greater than the activation energy. So you've got to get those molecules moving to that activation energy so that they can overcome that barrier. So larger fraction of molecules with with that higher energy to have that activation energy, you're going to have a higher number of collisions, leading to more product formation and a higher rate of reaction. So let's look at this equation here. K is equal to AE, and that is the just normal E in your calculator, to the negative activation energy over RT. This is called the Arrhenius equation. Good old Arrhenius. And that's really what we're after here. A is a constant called the frequency factor, and this really just depends on the reaction you're looking at. It's related to the frequency of collision and the orientation. A lot of times it equals 1, and yeah, we'll look at it later. The rate constant, that is the same K that we have talked about, our good old rate constant. It is dependent on the activation of the reaction and the temperature. So if we have two different reactions at the same temperature, they're each going to have a different activation energy because they're different reactions. They're going to need different amounts of energy for the reaction to occur. Now, if we have the same reaction at two different temperatures, we have the same activation energy. Okay, so the activation energy has to do with the reaction, not the temperature. So looking at activation energy, if we're looking at the number of molecules versus kinetic energy in these plots, the area under the curve is directly proportional to the number of molecules that possesses those energies. Okay. So in A, we have two different activation energies, so probably two different systems. We have this one here and this guy. So you can see at the lower activation energy, more molecules, so the area under the curve, that tells us we have more molecules that are at that energy. Whereas if we have something with a higher activation energy on this curve, it's a much lower fraction of molecules that are at that higher energy. Now, if we go and change the temperature, so this is at some T1, or we have a different temperature, but same activation energy. So we have our T1 is less than T2. So T2 is a higher temperature. Okay, and so it changes what the curve looks like for our molecules. And we're looking at the activation energy, just 1 here. We see that T2 has overall more molecules because it's this whole area. Okay, whereas T1 is just this smaller area down here. So you can also see then how increasing the temperature gives us more molecules at that activation energy. So now let's take the Arrhenius equation. These are both different ways of writing it, by the way. And we take the natural log of both sides, so that way we can pull this exponent down. And so then we get that the natural log of K is equal to the negative activation energy over R times 1 over T, or you could also just write that as negative EA over RT, is probably a better way to write that, plus the natural log of A. Actually, no, it's not a better way to write that. Leave 1 over T separate. The reason I'm saying leave it separate, we've been doing lots of linear equations, right? They're back. Natural log of K. So remember that K is temperature dependent when we talked about it before. So y equals mx plus b. There it is again. So if you make a plot, you have the natural log of K on the y-axis and 1 over temperature. And your temperature has to be in Kelvin. Okay, so 1 over temperature in terms of inverse kelvins. You will get a straight line. And the slope of that line is equal to negative activation energy over R. There is also a form of the Arrhenius equations where you can look at 2 K values and 2 corresponding temperatures. So there you go. Also notice that A is nowhere to be seen in this equation. Okay, so this type of equation does not use A. But you also have to make sure that the units for your activation energy and your R constant are identical. Which reminds me, I forgot to mention that the R that we are using here is 8.314 joules per mole Kelvin. So let's go ahead and look at an example. Variation of the rate constant with temperature for the decomposition of hydrogen iodide to hydrogen and iodine gas is given here. What is the activation energy for the reaction? So we're given some data of our temperature in Kelvin and our K constant, and we want to graph it. But remember, for our equation, we're not looking at just temperature versus Kelvin. We need the natural log of K is equal to negative EA over R times 1 over T plus the natural log of A. So we need to do 1 over T and the natural log of K, because that's what we're plotting. So 1 over T, we get 1.80 times 10 to the negative third, 1.74 times 10 to the negative third, 1.55 times 10 to the negative third, 1.43, and 1.28. Okay. And then the next thing is the natural log of K. So we get negative 14.860, negative 13.617, negative 9.362, negative 6.759, and negative 3.231. All right. So now we got to go ahead and do some plotting here. So the y-axis is the natural log of K. So at the top, let's see, 3, 6, 9, 12, 15. All right. We have negative 3, this is going to be negative 6, negative 9, negative 12, negative 15. And on the x-axis, 2, 3, 4, 6, 7. We're going to do 1.25, 1.50, 1.75, 1.80. Not ideal, but that'll work. And these are all times 10 to the negative third. So this is 1 over t. Okay, so when 1 over t is 1.8 times 10 to the negative third, so that's over here, our natural log of k is equal to negative 14.860. Right about there. And then 1 over t is 1.74, so right about here, at negative 13.617, so right about here. And then 1.55 and negative 9.362, so there-ish. No. And then 6.7 goes with 1.43. And the last one, 1.28, and that is negative 3.21. So there. My graph looks awful. This is supposed to be a straight line, not a curve, I promise. I promise it should be a straight line. I'm just going to go ahead and go on the next slide. I'm sorry, I suck at trying to do that. So there we go. There's what it should look like. This nice, pretty straight line. So if you remember, the slope of this line is equal to negative EA over R. And we're looking for EA. So the slope is equal to negative EA over R. So let's go ahead and find the slope of our line. So we're going to pick 2 points. We'll go ahead and do our first and last point. So our slope is equal to 14 point, sorry, we want to do, change in y, 14.860, or negative 14.860, minus negative 3.231, divided by 1.80 times 10 to the negative third, minus 1.28 times 10 to the negative third. So that gets you 2.2 times 10 to the fourth. And then that ends up being Kelvin, 1 over inverse Kelvin. Since the units up top, natural log of K, there's no units there. So 1 over K. So now we have Kelvin. And that is equal to negative EA over R. And we know R is equal to 8.314. So we're going to multiply both sides times R. Where was I? Oh, I lost my place. Oh, sorry, this should be negative 2.2 times 10 to the fourth. Okay, so we can see our negative signs cancel out. And so now EA is equal to 2.2 times 10 to the fourth Kelvin. Times 8.314 joules per mole Kelvin. So Kelvins cancel. And then this now is equal to 1.8 times 10 to the fifth joules per mole. Or you could say it is 180 kilojoules per mole. So that is how we can find activation energy from a graph.